Alright, first is the base for the transportation. We wanted some good wheels, as Evan said, that could go over all terrain that would be required. Then we had the handle for the cart style, as Evan also said, and designed that out of the same metal parts as the rest of it. So the support for the pitching machine was we had the little, we got our beams that I was pointing out, and then the rotation in the middle is, we have a shaft going through there that allows it to all rest on there. There's two bearings on the top and the bottom of that base plate, which we call it, and those bearings make it so that the shaft doesn't move at all when it's, because it has all this weight on it with sort of different bad angles that make it hard to rotate. So the double bearing makes it so the bearing doesn't fall out of its handle. The shafts are 1.25 inches thick, and we got all these pieces from Baumgart. They're generally tractor parts, I believe, but we just used 4 of those bearings. We also used 2 of them on top for the other rotation. And the actuator is what controls the rotation around the bottom. We call this one the horizontal actuator for how it's positioned. And it can extend, it goes just around the bearing so that it can, doesn't get it, and then also will be underneath it so it's out of the way. In designing these actuators, we had to take into account a lot of different factors to find the best setup that won't break, and it'll also be able to get our full range of motion. We wanted the horizontal to be the full 90 degrees of the field, and then also the vertical motion, we wanted to go from about -15 to just below 45 degrees for full span to get the furthest distance in the field. So through this we did calculations with our MathCAD program, and we're able to calculate the forces that would be exerted along with the different geometry that would work with the setup of the actuators that we had. We have the 18-inch stroke actuator for the height, and then we have a 6-inch stroke actuator for the horizontal one, with different load capacities. One is about 600 pounds for the bottom one and 485 for the top one. We also calculated the stresses in some of the key parts, such as the connection between the vertical actuator and the pitching machine. It has to go at a bunch of different angles, and it has to hold the whole weight right on the connection. So we calculated the stresses and determined a factor of safety of at least 2. We just put 2 in there because that was our goal, and we met that.
Okay, I'm going to go into some of the electrical design. I'm going to talk about, I split my design into basically 5 main components, which include the microcontroller and programming, interface and enclosure design, power design, wireless control, and other mechanical controls. First off, the microcontroller and programming. I used a Motorola microcontroller and programmed it in assembly language, and it basically is the brain of the pitching machine, and takes instructions from the user and puts them out to tell the machine what to do, where to throw the ball and when to throw it. Secondly, the interface and the enclosure. You can see the enclosure strapped here on that's pretty much my work right there. The interface is on the front and readily accessible to the user. It has, the main features on it are a large, fairly large LCD screen, which is used as a menu for the user to tell the user where they are in the program and what their options are. It also has several buttons, lights, and some LCD digits which inform the user of various things. They're located on the baseball field. You can see it also at the bottom of the screen. The buttons and such are located at each of the positions on the baseball field so that it's easy to know, like for example, if you want to throw the ball to center field, just press the center field button. It also contains the panel from the old pitching machine, which allows you to use the same options that you had before, like the speed knobs and the switch to turn the machine on and off. And the box also contains all of the electronic and power equipment that goes with the electrical design. Next, I'll talk about the power design and the wireless control. The power design uses two power supplies, which supply with plus and minus 5 volts, 12 volts, and 24 volts, which basically just do various functions. It also has fuse connections on each of those voltages and an emergency stop button for safety. The wireless control we wanted to develop so that while you're out in the field, you can tell the machine when to go and when to stop, so that you don't have to run back to the machine every time you want it to pitch another ball. What we found is a transmitter and receiver pair that have a range of over 500 feet, which was important because we wanted it to be able to be accessible from the whole field, which is just over 300 feet at the outfield walls. Next, the mechanical controls. It takes like I said, it takes information from the user and then controls various things in the mechanical design. So one of those things is the speed control. It controls the speed of the wheels. And this is kind of a small schematic of it on the right, just to get a little basic idea of what's going on there. It uses what are called Zener diodes, power transistors and resistors, and relays to do that. Secondly, it also controls the linear actuators, as Avery and Evan both talked about. Basically tells them when to extend and detract. Here's the breakdown of our budget. From the original research that we did, we estimated the total to be between about $1,300 and $1,400. Basically, like all budgets, we had items that we didn't account for in our original design, and a few that we did that we didn't actually end up needing. So it almost came up to be close to even, but I think Evan's going to talk a little bit more about that.
Yeah, all right. A few things that helped us out is we had, like Brian said, some things that we accounted for costing money, like the actuators, but they ended up actually being donated. So that's very nice. They're donated by Link. And one thing we originally accounted for is that we thought we were going to make the parts, but once we started designing, the parts became a little too complex and out of our machining ability, so we had to take them elsewhere. So that cost was a cost we didn't initially prepare for. And as you can see, Brian showed you the rest. Now to the acknowledgement. We'd like to thank the engineering department